Hello, Physics 1. All right, so welcome to part 1 of Tuesday's lecture, week 16. Guys, we're nearly there. I can smell the end of the semester. I think this semester smells like burning rubble, but it will be behind us. You will conquer. Okay, so we are continuing on in chapter 7, all about collisions. And we're going to talk about discovering the nucleus inside the atom. All right. As I've said before, this was a scattering experiment. All right, so this was the Rutherford experiment we talked about last time. Shooting alphas at gold. Okay, so one thing to know about this particular experiment, the alphas did not actually make contact. It was an electric force. So, essentially you've got the alpha coming in towards the gold, and then it's repelled, and the gold recoils a little bit. So this would be a collision, not head-on. Obviously, if it comes head-on, no, there'd still be probably enough repulsion that they would never actually make contact. So, we're in particle land, so that means that things can be fully elastic. So these were indeed fully elastic. So the quantum states on the nucleus were not excited. So pretty convenient when you think about it. And by the way, this was before they knew about quantum states of the nucleus, so Rutherford actually got very lucky. Or you could also say very fortuitous, or perhaps providential. I'll let you make a call on that. So, as a result, this is an easy analysis. So, Rutherford got lucky. Okay. So let's start analyzing the collision interaction. As these particles, made of charged particles, get closer, we start to see electric potential. So basically we've got our little alpha gun. And we have our region where the gold foil is, and you'll have kind of this area around it where you're going to be close enough to have electric potential. So U electric is approximately 0. U electric is approximately 0. And if you go from here to here, delta U electric is approximately 0. But in here, if you were looking at any interaction in here, you would have electric potential. So you'd want to know where you're analyzing from. So electric potential, as we know, is proportional to 1 over r, like gravity potential. And so how does the alpha interact with the electron? Okay, so we've got an alpha. It's a pretty beefy particle compared to our, and that is not to scale, our little bitty electron. So let's say it starts at rest, and basically if the alpha hits it, it's going to go, ah! It's kind of like that bowling ball marble example. So only much more extreme. Like this is 4 or 5 orders of magnitude more massive than the electron. All right, so in other words, we don't really need to think about electron interactions. So we can start inside the atom. So remember, atomic diameter is approximately 1 times 10 to the minus 10 meters, and the nuclear diameter is approximately 1 times 10 to the 14 meters. So let's start the analysis. So we want it to be inside of the atom, not quite at the nucleus. So we can start the analysis. When particles are about 1 times 10 to the minus 12 meters. So the electric potential at this distance is so here is our alpha, here is our gold over R. So we can plug in our values. So 9 times 10 to the 9 Newton meters squared over C squared. 2 times 79 times 1.6 times 10 to the minus 19 coulombs squared over 1 times 10 to the minus 12 meters. So all we did there was just bring the 2 and the 79 together and the 2 e's, e squared. The electric potential is equal to 3.6 times 10 to the minus 14 joules. Well, let's convert it to EV, which is far more useful. 1.6 times 10 to the minus 19 joules is equal to 0.2 times 10 to the 6 EV. The electric potential is equal to 0.2 MeV. That's why we left it like that. All right, so in the Rutherford experiment, the alphas had a kinetic energy of 10 MeV. So for this separation, if we wanted to look at, you know, a collision within the margin where there is electric potential, electric energy is only 2% of the kinetic energy. So, really, the only significant changes we're dealing with are going to be due to kinetic energy, which makes, like I said, the analysis of this particular experiment pretty straightforward. So even if you were looking at, say, going from 1 times 10 to the minus 12 away from the nucleus to 1 times 10 to the minus 12 on the other side, delta U electric, in this case, is just 0. So we can do on only kinetic energy. And further, you can be pretty assured that the alpha is only going to hit one nucleus because gold nuclei are 2 times 10 to the minus 10 meters. So the alpha isn't going to hit another. They're pretty spread out. I mean, remember, you are mostly empty space, and so is gold. So this is way bigger than. All right, so I've hopefully justified to you why we can do a relatively simple analysis. So analyzing the kinetic energy changes and scattering angles. Remember, you can get momentum from kinetic energy changes. Led to the discovery and the disproval of the plum pudding model. All right, so there you go. Moving on. Relativistic momentum and energy. So far we have been staying in classical land. We can do these things relativistically as well. I mean, that they do them relativistically at the LHC. Let's do them relativistically, I would say, in our Northwestern classroom, but I'm in a Northwestern classroom. Maybe you are on a beach someplace. More than likely in a room, in a house full of people who would like to be outside. All right, so the Rutherford experiment was classical. And that means low speeds, low energies. Modern particle accelerators can have speeds upward of 99.999% the speed of light. And these accelerators are always getting faster. All right. For this, we need a relativistic update. So, M1 has momentum 1 going towards M2, which has momentum 2 of 0. All right, so what can happen, then you'll have, it gets even more complicated. You often have an identity change too. So you have M1, M2 leading you to M3, M4, maybe M5, and the different scattering angles and momenta. I mean, after all, we discover new particles by crashing things into each other. Basically, we are just a bunch of small children who just never stopped loving destruction. Okay, so let's write down some relativistically correct equations for momentum conservation and energy conservation. All right, so for this, we are going to need E squared minus PC squared is equal to MC squared squared. So the energy equation that works for everything. So see how E and P are related. I mean, even if you've got a massless little photon, you can use this equation. You just don't have an MC squared term, it's just 0. And then in that case, E squared is equal to PC quantity squared. Okay, so from here, momentum 1 is equal to P3 cosine theta plus P cosine B. That's X momentum conservation, which means next up we have Y momentum conservation. 0 is equal to P3 cosine 90 degrees minus theta, P4 cosine 90 degrees minus phi, y momentum. Conservation. E1 plus m2 c squared is equal to E3 plus E4, and this is energy conservation. And recall that it is scalar. And we can update the energy equation with momentum. So let's do that. P1c quantity squared plus M1c squared quantity squared plus MC squared is equal to P3c squared plus M3c squared squared plus P4c squared plus M4c squared quantity squared. So all we've done to get this is we have used this relationship and we have plugged it in to here. So, same as before. 4 unknowns, 3 equations. And like I said before, at least one additional quantity is measured, and the rest are calculated. And as I've said before, and I'll write this down, has different areas measuring different properties. And further aside, that identity change is fundamental to how we understand particle physics. Okay, so I've already alluded to this. Let me state it again. Photons have momentum. And photons play a role in relativistic particle physics. After all, they are the charge carrier. So, these have momentum as well. E squared minus PC squared is equal to MC squared squared demonstrates mass is not needed for momentum. I mean, we've already seen it's impossible for a massive object to travel at the speed of light. So, a photon with energy E has momentum equal to E over C. And this has been confirmed. Through rigorous experiment. But of course, please note, do not use E is equal to gamma mc squared or P is equal to momentum or gamma mv for photon momentum. Those equations are for massive particles only. There we go. Okay, so I am going to stop. No, I'm not. Let's do an example. Okay. What I am going to do is pause and sit in a chair. Okay, so a photon with energy E is absorbed by a stationary deuteron. This breaks into a proton and neutron. And this happens at V much, much smaller than C. So here's our deuteron. There's the photon going towards it. And now we have the momentum of the proton and the momentum of the neutron. Actually, I named this angle alpha in my notes. I will stick with alpha, because you can name angles whatever you want. Okay. The angle theta is observed. So in this particle detector, they have been set up to measure the theta scattering angle. So what we want to do is write the equations to solve for unknowns. The proton momentum, the neutron momentum, and alpha. To the direction of the incoming photon. We're going to use MD, MP, and MN. We know the mass of deuterons, protons, and neutrons quite well. We don't need to measure them. They're not unknown particles. And we're not going to solve the equations. But you could. All right, so here's our setup. Here's what we need to do. Now let's start going for it. So our system, all the particles. Surroundings, nothing. And we have momentum conservation. P gamma is equal to P proton plus P neutron. So we have E over C, 0, 0. P proton cosine theta plus P neutron cosine alpha for X. P proton cosine 90 minus theta minus P neutron cosine 90 minus alpha and 0. There's my vector on 3 lines. So from here we have E over C is equal to, this is, by the way, conservation of momentum, not energy. So proton momentum cosine theta plus proton momentum neutron cosine alpha and 0 is equal to proton momentum cosine 90 minus theta minus Pn cosine 90 minus alpha. So all I've done there is break this equation into its individual components. So, all right. So that's as far as we can get with momentum conservation. Let's look now at energy conservation. So energy plus m deuteron c squared, because remember photons are pure energy, is equal to the mass of the proton, c squared plus 2mp, so this is rest mass plus kinetic energy, plus neutron c squared plus the momentum of the neutron 2 over the mass of the neutron. So we have 3 equations and 3 unknowns. So remember, theta was measured. So you could solve this. It would take some algebra, but it is very, very doable. All right, so a couple things. You could solve with some algebra. Not even calculus, just some good old-fashioned algebra will do. And note, we could have also done this with relativistic equations. Using so we could have used E squared minus PC squared minus MC squared quantity squared, which means E is equal to so then you'd have E plus the mass of the deuteron C squared is equal to So what I have here then, this is the relativistic energy equation for the proton, and we have the relativistic energy equation for the neutron. That would have also been correct to do that. And of course, this is how we discover new particles. So, for example, let's look again at neutron decay. So we observed neutron decay. So neutrons decay into protons plus electrons. And this violates the momentum and energy conservation. So we've observed that for a while, that a neutron by itself decays in about 15 minutes time into a proton and an electron. Neutrons need to be in nuclei if you want them to be stable. So that means if you see that the momentum principle and the energy principle has been violated, something else is produced that you are not measuring. So something else has been produced. And the solution to that is the neutrino. So, the neutrino's existence was speculated long before its discovery because of this missing energy. And so, if we want to do a Feynman diagram, which of course we do, for this, you've got your neutron, so this is an up quark, a down quark, and a down quark decaying to up, down, up, which is a proton. And so then you have your W minus boson. That's your weak force carrier. And we have the electron and the anti-electron neutrino. And there you have it. Energy and momentum principle being used and applied to do new physics. Fundamental principles, been around for a while, still in use today. Okay, so let's look at inelastic equations and quantized energy. So, Rutherford had it easy. He excited gold nuclei, or he did not excite the gold nucleus. And had elastic collisions. Way easier to analyze. But sometimes we don't get so lucky in life. So, what would have happened if the experiment had been repeated under inelastic conditions? So we increased the internal energy, so delta E above ground. So you've got your M1, momentum 1, hitting mass 2, which starts at rest. So we know incoming P1 of alpha, and we measure outgoing momentum of the alpha and scattering angle. Let's go after momentum and energy equation. And we cannot assume that this is non-relativistic. So, just to note, recoiling nucleus will have energy m4c squared plus delta E corresponding to the excited state. So then you have P1 is equal to P3 cosine theta plus P4 cosine phi, where that is the gold. And then you have 0 is equal to P3 cosine 90 degrees minus theta minus P4 cosine 90 degrees minus phi. And so, I'm running out of room. E1 plus mc squared is equal to E3 plus E4. E4 is equal to P4c squared plus m4c squared plus delta E squared. So 3 unknowns, P4, phi, delta E, 3 equations. We could still do it. And that concludes chapter 10 on collisions.